Welcome to Brain Vision.
Okay, so in this question, we have kind of a weird setup. We have a string that is attached to a surface at the bottom, and the top end is kind of attached to this metal cart that is able to roll around. And so the top is able to move freely. Um, so it's a little bit of a weird setup, but that's honestly the most difficult part of the problem. The rest of this is pretty simple stuff that you've dealt with throughout this chapter. So the mass of this string, sorry, is equal to 5.50 grams, which of course is 0.00550 kilograms. The length of the string is 86.0 centimeters, which is 0.860 meters. And we're also told that we can assume that there's a constant tension in this string of 1.30 newtons. And in part A, we're asked to find the speed of transverse waves in this string as it moves. And so this is pretty straightforward part. We just need to remember that the speed of a wave in a string that's under tension is going to be equal to the square root of the tension force divided by mu, which is mu, of course, is just equal to the mass of the string divided by its length. So then our formula just becomes T times L over M. And if you look at the variables that were given straight away at the beginning of the problem, they are M, L, and T. So we have everything we need to do to solve this part of the problem. So we just go ahead and plug in everything. So our calculation is the square root of 1.30 times 0.860 divided by 0.00550. And if you calculate that out, you should get the speed of the waves is 14.3 meters per second. So that's our answer for part A. And then in part B, we're asked to find the node to antinode distance for the three simplest modes of vibration. So that means for the first three modes of vibration, we want to find the distance between a node and its adjacent antinode. So to do that, it would be helpful to draw the first three modes of vibration. So we're told in the problem that the end that's attached to the platform at the bottom is going to have a node, and then because the top end that's attached to the cart can vibrate freely, that's going to have an antinode when it has a standing wave. So if we draw that the way that we draw like sound, the same way that we draw like sound waves and other standing waves that we've done with this book, the first node is going to have, or the first mode of vibration is going to have a node at one end and an antinode at the other end of the string, which gives us a diagram like this. And so the distance from a node to the adjacent antinode is, of course, just the full length of the string. So for the first one, I'm going to number these just 1, 2, 3. For the first one, where the node antinode distance is just L. And then for the second mode of vibration, we need to add a set. We have to add another node in between there. So our drawing is going to look like this. And that's not quite to scale, obviously, but we do know that from a node to an antinode and from an antinode back to a node, all those distances are going to be the same. So we have a node going to an antinode. That's 1. I'll draw this in a different color, actually. So that's 1. And then from an antinode back to node, and then from a node to an antinode. So we actually have 3 lengths. These should, if I drew this accurately, these would actually be all the same size. But that means that the node to antinode distance from here to here is going to be 1/3 of the length of the tube, so L over 3. And then we just do this again for the third mode of vibration. And so we just add another node in there before we get to the end of the tube. So it'll look like this. And I'll draw one more time. So we have a node to an antinode here, antinode to a node to an antinode to a node, and then node to the antinode again. So we have 5 lengths now, 5 distances of a node to an antinode. So that means that the node to antinode distance is 1/5 of the tube, so L over 5. So for the 3 simplest modes of vibrations, the node to antinode distances are L over 3, and L over 5, which then we just need to calculate out. So L, of course, is still 86.0 centimeters. And then L over 3 is equal to 28.7 centimeters. And L over 5 is equal to 17.2 centimeters. And I feel like all of that is self-explanatory. You just take 86, divide by 3, and divide by 5. So these are our answers for part B. I don't feel like that needs much more explanation than is there. All right, and then in part C, we need to find the frequencies for each of these 3 modes of vibrations. And this part is also fairly straightforward. We're just doing, the same calculation 3 times. So of course, F is going to be equal to V divided by lambda. And lambda is going to be, in this case, 4 times each of the lengths that we had in part B. Because the distance from a node to its adjacent antinode is always 1/4 of the full wavelength. So we just take these 3 distances, 86 centimeters, 28.7 centimeters, and 17.2 centimeters, and we multiply them by 4 to get the wavelengths for each of the 3 modes of vibration. So if you want to, you can also calculate it directly from the length of the tube, or not the tube, the length of the string. And if you do that, you will say that, for the first mode of vibration, the wavelength is going to be 4 times L. For the second one, it's going to be 4/3 times L, and for the third one, it'll be 4/5 times L. And that's what I did when I was calculating this out. So that is how I'll write it. So for F1, the frequency of the natural frequency, the first mode of vibration, you'll have 14.3 for your speed. And then in the denominator, you have 4L is equal to the wavelength. So you have 4 times 0.860 meters. And if you calculate that, you should get 4.14 hertz for the first mode of vibration. And throughout this problem, it's important that you carry all the decimals until you get a final answer, because as we're building on our previous work so much, if you make a rounding error, it will compound as you go through your work, and it will make your answers in part C a little bit off. If you round, if you don't carry all the decimals through. So that is the frequency of the first mode of vibration. And for F2, we have 14.3 still for the speed of the wave. And then this time, the lambda will be 4/3 L, which means that if that's in the denominator, then there's going to be, you take the reciprocal of multiplying by taking the reciprocal. You can say that it's times 3 in the numerator and then 4 times 0. in the denominator. So we end up with just an extra 3 in the numerator. And then your frequency for the second mode of vibration is going to be 12.4 hertz. And for the third one, last but not least, F3 will be equal to 14.3. And now the lambda is 4/5 times L. So we end up with a 5 in the numerator because lambda is in the denominator. So, and then you end up with 4 times 0.860 in the denominator one more time. And so if you calculate that out, then your frequency for F3 should be 20.7 hertz. And then we are all done. There you go.